So welcome everybody to this European Tensor Network colloquium. So it's a great pleasure and honor to have Donna Sheng to give a talk tonight. And she is from Cal State Northridge and has been one of the driving forces in using density matrix renormalization group studies on interesting materials, actually also two-dimensional materials, quantum Hall. So lots of very fascinating and interesting things. And we are all looking very much forward towards her talk. So please, Donna, the stage is yours.
Thank you, Frank. It's a great pleasure to be here. So I'm going to talk about the density matrix renormalization group study of doped Mott Insulator and square lattice. So that work is done in collaboration with Su Gong and Wei Zhu. Both were postdocs in my group, and we kept collaborating since then, and research is supported by Department of Energy. Oh, here. So that is the outline of my talk. I'll first give a very brief introduction about the high TC Cuprates as the doped Mott Insulator, and discuss some of current numeric works. Then in the second part of my talk, I present the global phase diagram based on our recent DMRG study of TJ model and cylinders. I'll show you that we have identified 3 different phases, including 2 of superconducting phase. One is uniform d-wave superconducting phase. The other one is superconducting coexisting with charge density wave phase. Then I show you how robust your superconductivity is in those 2 phases. Because this is a quasi-1D geometry, we do not expect a non-range order due to the Mermin-Wagner theory, but we can recognize the superconducting correlation in terms of power law, and the power law exponent turned out to be much smaller than 1, indicating a very strong correlation. Then I will summarize my talk. So high temperature superconductivity was discovered almost as 40 years ago. The critical temperature is as high as around 140 degrees. It remains to be the highest among different classes of superconductors. And the most remarkable properties of this high TC superconductivity may not be the only superconducting states and the high critical temperature. The normal state turned out to be very interesting. So in experiments, you can raise the temperature to go to normal state. The Fermi-degenerate temperature for Cuprates is determined by Fermi energy, which is around 100,000 Kelvin. So you have a huge room to measure the normal state property. And some typical experimental results can include the specific heat measurement, Pauli spin susceptibility, and also NMR, spin lattice realization rate. If we have a Fermi-liquid, then we expect the linear T dependence for specific heat and the constant Pauli spin susceptibility, as well as that's 1/T1 proportion to temperature. So if we look at experimental results, it's very clear that those measurements do not follow the Fermi-liquid behavior, including that the specific heat, the coefficient gamma for the linear T-dependent is dependent on temperature. It shows the linear T-dependent. Gamma itself depends on T, which is modulus linear with T. Then the Pauli spin susceptibility also shows temperature dependence instead of a constant behavior. Because the temperature is around 200 Kelvin to like 60 Kelvin, it's much, much smaller than the Fermi degeneracy temperature. So if we have Fermi liquid as a starting point, then we expect those red lines for the 1/T1, the rate, that's 1/T1 rate first jumps out of the superconducting phase, then it remains like a constant in a wide range of temperature, also opposite to that linear T dependence. Those indicate we are looking at a non-Fermi liquid normal state. The importance of understanding normal states have been emphasized by different theoretical work. Another point of important point is if we go to half filling, which is the parent state of high TC cuprates, before we do the electron or hole doping, then we have antiphase magnetic order. And the superconducting phase also has incipient charge density wave. So those indicate we have a very strongly interacting system, which give us the antiphase magnetic ordered Mott Insulator at half filling. So Phil Anderson first proposed a theory for high TC cuprates as doped Mott Insulator, which becomes the starting point for a lot of theoretical and numerical studies. A good model, the simplest model which can capture the doped Mott physics is the one-band Hubbard model. It's not realistic, but it can be the good starting point to discuss the physics if superconductivity can emerge from a pure repulsive model. So the Hubbard model at large U naturally give rise to the Mott Insulator, because with the increase of U, we need to project out the higher energy band with double occupancy. Then the picture of doped system can be understood based on sorry, I don't know the side panel how to get rid of it. So anyway, the doped Mott Insulator can be understood based on doping the TGM model. You're taking out the hole in the projected Hilbert space without double occupancy. The Phil Anderson picture for superconductivity has a very simple picture called the resonating valence bond theory. So at half filling, as a good starting point, is the all the pairs of spins form the singulates. Then with doping, those singulates can move around to give rise to pairing condensation and the superconducting phase. There are also other pictures. For example, Zheng Yiveng proposed that phase string theory the starting point is for doped hole, there will be a spin texture around the doped hole. So maybe dressed hole can form the pairing. There are also a lot of theoretical progress towards understanding the pairing in the pure repulsive model based on the resonating valence bond picture, slave particle mean field theory, as well as the gauge theory. Variational wave function actually give out very positive results about the simple picture of RVB, RVB theory. However, since we have a very strong correlated system, then there is no analytical solutions to the mesoscopic models. So we need numeric studies to provide the proof of principle results and further understanding of those systems. Many different methods are applied to this system, including exact diagonalization, quantum Monte Carlo dynamic mean field theory, and tensor network approach, including DMRG and PEPs. Because this is a strong correlated two-dimension system, so we do not expect one have a real good method which can solve this problem. So combined study provides more insight into those models. So before we go look at more detailed numeric results, I want to give a very brief summary of what have been established based on numeric study. I think the common features of studying Hubbard and TGM model is that the charge density wave is often one of the most important order in the ground state. And depend on the doping level, sometimes spin density wave can also compete with the charge density wave. Based on the different combined methods, there is a conclusion about no superconducting phase for TJ and Hubbard model with only nearest label hopping. So that model I will refer to as a simple TJ and or TU model. Then superconducting correlations in some more extended models, sometimes we call it a TT prime J or T1, T2 J with further label hopping. Then in that extended model, your superconductivity can compete with other orders in the form of stripe and superconducting coexisting. So let's look at some detailed numeric results. Here I show the early DMRG results from Hongchen Jiang for the TJ model and the full leg ladder, so that demonstrated there is super power law decay of superconducting correlation, and also the superconducting order parameter has the d-wave-like symmetry, in the sense that if you use the superconducting correlation to map out the sign of the pairing order parameter, then all the pairing along the x direction has the same sign as indicated as the blue line here. Then all the correlation along the y direction actually has a vary of the sign. So if the correlation is in the same the order parameter is in the same column, then the sign is positive. When you shift the one bond in the y direction, you get the negative sign. So that is not a uniform d-wave symmetry. The superconducting quasi-long-range order has an exponent around 1, and the density correlation has a similar power law behavior. More recent work by the same group focused on the 6-leg ladder and the comparison with the 4-leg ladder with a large T2. The T2 over T1 is determined by the square root of J2 over J1 in their model. So their model has both Lex nearest label hoppings and Lex nearest label spin Heisenberg interaction. So they look at that point as at J2 over J1, there is a possible gapless spin liquid on the square lattice. So their results demonstrated the power law behavior of superconducting correlation for both 4-leg ladder and 6-leg ladder. As they increase the cylinder width, the power law behavior decay with a similar rate. The exponent is still around 1, and that is a phase in quantum 1D known as Luther-Emery liquid with competing superconducting and CDW ordering. Tendency of superconducting and charge density orderings. So I showed a picture here. I showed a picture here that T1 is the nearest label hopping and T2 is the Lex nearest label hopping. J2 is the Lex nearest label Heisenberg hopping. So that is the same model. I will present our numeric results. Another picture, recent picture is obtained by John, Scalapino, and White based on a local probe from DMRG focused on the local quantities by breaking the symmetry. So for that picture, they studied a wider system with up to 8-leg ladders. So the reason they can study much wider system is because we believe the local quantity are much easier to converge than look at the long-range correlations. So if we do the DMRG study for a magnetic ordered system, we all have this experience. The spin SU2 symmetry will spontaneously breaken. And here they found for the I think it's a TGM model. For the TGM model, the U1 symmetry can also break for some parameter region. So their phase diagram has parameter T prime, which is the Lex nearest label hopping. For the positive T prime, in different doping regions, they have different phase. But overall, they are d-wave singlet order parameter and p-wave triplet pairing. The p-wave triplet pairing is an effect as they also find the antiphase, local antiphase magnetic order. Then the stripe is also coexist. Especially in that region with doping level around 15 to 20%. For the negative T2, they obtain the different stripe ordered phase with increasing doping. And in this local probe, you can also gain the insight of where are the doped holes, what kind of configurations of pairing are more easily are more commonly to appear. So I think it's a very interesting probe, especially if we want to study wider systems. The earlier PEP study also find something similar in the sense that as the next nearest label hopping versus the nearest neighbor hopping, this ratio is varying. You can get different competing states with one state with a different period of stripes. In some regions, they also have weak superconducting order parameters, indicating stripes coexist with superconducting quasi-long-range with superconducting order. Then I want to also cover this work by the many-body collaboration, which gives the conclusion that there is no superconductivity for the nearest label Hubbard model. Another very insightful picture is from the quantum Monte Carlo. When you start from the variational Monte Carlo, using the BCS trial wave function, so you started from very large superconducting the pairing correlations. With the improving of quantum Monte Carlo, with improving the state, the superconducting correlations get suppressed. I need to mention that model with doping, we have sign problem. So the quantum Monte Carlo has to deal with the sign problem. They either use fixed nodes approximation or use brutal force to deal with the sign problem. Then one probably can limit to lower doping level, but I'm sure there are also technical development for quantum Monte Carlo, but that system does have the sign problem. So let me move on to the second part of my talk. I want to present a global phase diagram for the extended TGM model based on the SU2 DMRG study. The main results are presented for 6 leg cylinders. And we also compared the results with 4 leg ladders. So the model I will refer to as T1, T2, J1, J2. So that is different from some of the previous study where they considered T1, T2 and near this label Heisenberg coupling. I think the second J2 is not so important, but we haven't checked the model without J2 yet. So the SU2 DMRG allow us to keep a band dimension around 20,000. However, those 20,000 are spin multiplets. So it represents roughly 60,000 U1 states. You see that we really need and would like to go to a little bit larger system because we are looking at correlations. The picture of the phase diagram is here in the parameter region of ratio T2/T1, as well as the whole doping ratio. The another parameter J2/J1 is determined as the square of T2/T1. So that is consistent with you start from a T1, T2 model and project into the TJ model. So we didn't change J2, J1 as another free parameters. The main results is we have 3 different phases. In that small T2 region, inconsistent with many body collaboration results, we don't find the quasi-long-range order for the superconducting phase. The only instability is the charge density wave instability. And in the ground state, the density actually shows the stripe. Then intermediate phase, we have very uniform charge density, and the charge-charge correlation function decays much faster than the superconducting correlations. So that phase, we label it as d-wave superconducting phase. Then we also have a coexisting phase where the superconducting correlation remain to be power law and very strong, but the charge density correlation is also has the quasi-long-range order. So another thing is in quasi-1D, we cannot really say they are different phases. You just see the power law behavior evolve into different region of exponents. So that phase diagram is a conjecture for the possible physics in the 2D. So there is a jump, but the best guessing is a phase diagram like that. Then I also want to compare that phase diagram with the phase diagram for the square lattice Heisenberg model with J1, J2. Because we only vary T2/T1 up to 0.33, which means J2 is only around 0.1 of J1. So we are always doping the antiphase magnetic ordered state. So spin back one at half filling was now changed by J2. So the main physics indeed should coming from the varying of next nearest label hopping. So let's first look at a sum of the electron charge density at a fixed doping 1/12. Then we change T2/T1 from 0 to 0.12 and to 0.22. At T2 equals 0, the charge density pattern is very robust in the sense the amplitude of the oscillation seems not decay into the bulk, or it actually decays very slowly. Then for the T2/T1 around 0.12, where the J2/J1 is around 0.014. In this case, the charge density changed to something very flat in the bulk. You see that there is almost no oscillation until we reach the sample boundary. Our system has Ly equals 6 unit cell, then Lx equals 64. There are also other results for Lx equals 48. Then we increasing T2 over T1 at the ratio of 1.22. We also see the stripe density pattern, but the period is doubled from the T2 equals 0 case. And also the amplitude shows smaller decay as we go to the middle of the system. So this result is a common feature of the superconducting and the CDW coexistent phase. However, the pattern, however, the pattern of this correlation, the amplitude may decay slower or faster, depends on where the parameter point is. I also want to point out the different period. This one has a period 8 for 1/12 fitting and doping level. It contains 4 holes in each stripe period. Then the bottom one has reduced the period, and it contains 2 holes in each stripe. So that's configuration at larger T2 is more favorable towards pairing. Then I also want to show you the corresponding pairing correlations. We first look at the symmetry of the pairing. We fix one bond near the sample edge, then vary another bond. We find the sign of pairing correlation depends on if you have 2 of Y bond, which give you positive sign. If you have 1 Y bond and 1 X bond, then the correlation is negative. We also look at 2 Y bonds, correlation between 2 Y pairs. The correlation is also positive. That indicates the order parameter has a uniform d-wave pairing, like one of direction have positive order parameter. Once you rotate 90 degrees, you get negative order parameter. We also look at the diagonal correlation that decay much faster than the X and Y bonds. So here is for T2 over T1 equals 0.12 at 112 finning. We plot those absolute value of those correlations. Since one of them, we plotted the negative sign of the correlation. The decay very slow. So for distance between 1 to the 30, they only decay by 1 order magnitude. For that one, we kept 20,000 states. And we also see how the pairing correlation changing with the parameter T2 over T1. The blue one, which drops very fast, which is about 3 to 4 orders faster than other pairing correlations. That is the simple TGM model without secondary label coupling. With secondary label coupling, the superconductivity jumps by that many order of magnitudes. The electron occupation number in the momentum space also show different feature with hole-like, with the closed Fermi surface for larger T2 over T1. But it shows symmetry breaking, lemmatic symmetry for the T2 over T1 equals 0 case. So that's kind of the NK is connected to this very strong CDW. But for the weaker stripe order, we do now see very clear picture from the electron occupation number. So before we look closer into the superconducting phase, I also want to show you the role played by band dimension, like what is the typical truncation ether and what is our energy before we do the scanning to the zero truncation ether limit. The energy for our largest band dimension is close to the extrapolated energy, and the scanning is smooth. Then we also follow Hongton-Jiang's analysis to do the scanning of physical quantity like a correlation. So the many body collaboration also did that kind of scanning. So you have the pairing correlation at different bond dimension. Then you do 1/d extrapolation to get the correlation at an infinite band dimension. So that scanning is extremely smooth for shorter distance. Then the scaled data has much enhanced pairing correlation for longer distance, indicating the loss convergence at a longer distance. Then we also show similar scanning of correlation, correlation for the density correlations. Before we examine the behavior of pairing correlation, I also want to compare the pairing correlation with charge and spin correlation. For our superconducting phase, for intermediate T2/T1, so both d-wave uniform phase and coexisting phase, we have pairing correlations decay at least 2 orders of magnitude. We have this correlation at least 2 orders of magnitude larger than the density correlations, and also much larger than gain function at the same distance, as well as spin correlation at the same distance. That picture remains to be true, but the correlations getting closer as we further increase T2/T1. We already mentioned we are studying this quasi-1D geometry. So we can now have the real non-range order. We can look at if the pairing correlations following the quasi-non-range order. So for the pairing correlations with different band dimension, we first plot them in this semi-log plot. You see almost straight line. That means even for our largest band dimension, we see the exponential decay of pairing correlation. But the correlation length increasing not linearly, parallelly with band dimension. And also at our largest band dimension, the correlation length for pairing is about half of our system length. And it has the trend of divergence with band dimension. Then we also look at the log-log rhythmic plot. Then we see that at short distance, those correlations do follow very good straight line behavior. And it falls faster than parallel and longer distance. But with increasing band dimension, the correlations also enhance very fast at a longer distance. The scaled data at a band dimension equals infinity demonstrate a very good power law behavior, except at the system boundary. The exponent for this scaled data has power law exponent, has K for superconducting around 0.36. So we did the same fitting for the density correlations. It shows the power law behavior as well. And this power law behavior has an exponent KCDW around 3. So it indicates the correlation between those two exponents. For some of our points, those two exponents multiplied together has a value close to 1. And with very small K superconducting and a much larger K for the CDW. Yeah, so that's one. So that's KC means KCDW. So it's a special example of Luther-Emily liquid with possible only superconducting instability. We also compare the raw data from the cylinder width 6 with the data with cylinder width 4. The cylinder width 4 data decays much faster with a power exponent around 1 for superconducting correlation. For the density correlation, it has the opposite trend. The CDW gets more, the charge density correlation gets more suppressed with its power law exponent increase from 1.4 to 3.4. And, to something around 3. Then the D equals to 20,000 data shows a behavior very close to infinite bond dimension extrapolated data. So that is the point for the whole doping 112. We also look at the data at doping 1/8 and 1/6. Here is an example of doping at 1/8. We see the same exponential decay, exponential correlation length increasing with bond dimension with the trend of diverge. Then the scaled data gives the power law behavior for the superconducting correlation with the power law exponent still around 0.36. Then the CDW, the exponent for the power law behavior reduced to around 2. For the whole region, we identified as uniform d-wave superconducting phase. The superconducting correlation exponent is always around 0.36. I think for some data, it goes to 0.5. Then the CDW exponent is always much larger. So I hope that give us some confidence about the superconducting phase. The state we identified is has much stronger superconducting correlation than the one we mentioned of doping spin liquid from Zhang's group. Then we look closer at the CDW phase. The charge density always has a stripe pattern with the period vary, but it always contains 4 electrons inside the period. And the amplitude decay extremely slow. If we fit the amplitude decay, we get an exponent around 0.36 to 0.6 indicates very strong CDW order. And the superconducting correlation, I showed you one example. Now I show you the different doping levels. So now I show you both doping 1/8 and 1/12 at T2/T1 equals 0. They both decay exponentially with a shorter decay length, and those data are converged with larger bond dimension without power law, without the possibility of power law decay. Then the density, there is one thing we feel is a little bit strange, which is the stripe has a very robust pattern in the density. However, density correlation also decay exponentially. Maybe that's because the quantum fluctuation is not so strong, so the local density gives better description. So we look at a single particle and the spin both decay with a short correlation length, but the spin correlations are much stronger than single particle green function. And also stronger than density correlation. So that leaves the space for further going for spin correlation for wider system. Now we move on into the uniform phase. Just show you different parameters. We always have very uniform charge density in the bulk. We already discussed the robust superconducting correlations and compared the dominant superconducting correlation with spin and green function and density correlation. Now we want to look closer at the superconducting and the CDW coexisting phase. We label them as the same phase, but with increasing of T2, the charge density CDW pattern gets enhanced. We can look at the fitting of the amplitude decay, the exponent reduced with the increasing of T2. However, this exponent is always larger than 1. It's in the range of 1 and 2. So we think it still has the divergent charge susceptibility at T equals 0, consistent with a coexisting phase. We also look at more data of superconducting correlation in this coexisting phase. It really has very similar behavior as the superconducting, the uniform superconducting phase. However, the CDW power exponent reduced. Then if we look at larger T2, the power law decay for the superconducting correlation has an exponent close to 1, and the CDW exponent is also close to 1, but still slightly larger. So I think that phase is connected to the phase studied before with Luther Emery liquid by doping spin liquid with even larger T2. For the coexisting phase, we have fast exponential decay, single particle hopping. And the single particle hopping is getting decay much faster as we move from Ly equals 4 to Ly equals 6. I suspect that's related to gapness excitation for the single particle at the four-leg ladder, because related to possible nodal superconductivity. But that kind of behavior is not able to sing on a six-leg ladder. So it's very interesting to also study the eight-leg ladder. So let me summarize as part of talk with DMRG phase diagram. We identified CDW phase and the uniform d-wave superconducting phase, and d-wave superconducting and the CDW coexisting phase. It's kind of interesting to see that the d-wave superconducting phase expands with the increasing of doping level. Then we can have transition either from CDW to d-wave or from coexisting phase to d-wave, pure d-wave phase. Before I close my talk, I also want to mention a few Hall cases where there is something interesting, which is if we have odd number of Halls, there is always nonzero ground state angular momentum, which makes the ground state always degenerating. Besides the degenerating due to spin 1/2. This picture is being checked to be robust for larger system. To check that, we did up to 8x8 open system with C4 symmetry. If we consider 2 doped holes or even number of doped holes, the angular momentum of ground state is always 0. If you just plotting those degenerating states, you get a different charge density or spin density pattern due to the ground state degeneracy. But we do not understand the connection between that kind of spin currents and nonzero angular momentum and the pairing, which is something we want to explore in a near future. So I'll just stop here with this page about the summary. Thank you.
Thank you very much, Donna, for this great overview and very interesting results. So I'm sure there are some questions.
Maybe I could start with one. Well, actually I have 2 questions. Like, one is regarding the phase transitions. Is it from the data possible at all to make statements about the phase transitions and their nature?
For the Quansi 1D, after we submit the paper, we was reminded that there is no different quantum phases. There are maybe same phases, especially superconducting and the superconducting CDW coexisting phase, because they have power law behavior and the exponent just changed. But from exponent, you can conjecture if that phase has this non-range order in the 2D limit. So I think we cannot tell if transition is smooth, or we cannot really identify the signature of quantum phase transition.
Okay, and then a quick other question, like regarding experiments. I mean,
yeah,
if we just take superconducting compounds and we just tune, for example, doping, and maybe by in some way T1 and T2 are known for certain materials, do they fit into this phase diagram, at least qualitatively?
No, I think Steele's paper describe it very clearly. So we suspect for super Cuprates, the T2 is negative.
Oh, I see.
Yeah, but so far, I think all the numeric calculations has a lot of consistency between different groups. They always find we need a positive T2.
Mm-hmm.
However, maybe the minimum model is not good enough to address real connection with the experiments.
I see. Thank you.
Thank you.
So, so I saw that Tarun had a question.
Thank you. Very nice talk, Donna. I had a question about, can you give some insight into the spin current? Why is there a spin current around the hole? And
spin current around the hole is so we the angular momentum is non-zero for this finite cluster with C4 symmetry, and which is also consistent with what we know for the torus system. The one hole has total momentum plus minus pi/2. It has a high degeneracy. You can use them to get an angular momentum non-zero state instead of angular momentum equals zero state. So from if you just fix at one ground state with angular momentum equals +1, then you calculate a spin current is non-zero. The spin current is defined as like S dagger S, SI dagger S J.
Right.
Yeah. So that current is non-zero. However, this is just a picture based on finite size study of field holes.
I see. Can I ask one different question about, so if I take this, so let's say this is happening in 2 dimensions. I forget the quasi 1D picture. Let's just take a 2D system where this is a phase diagram. So which 2-dimensional spin liquid are you doping to get this?
Yeah, so our calculation has a very small J2. So we focus on doping the antiphase magnetic ordered phase.
Right, okay.
However, there is another work by Hongzhen Jiang and Kiverson. They used a much larger T2. T2 over T1 equals 0.7. So they are doping either a critical point or a gapless spin liquid. So they are current, it's controversial, but there are new DMRG work suggesting deluxe spin liquid for the Heisenberg J1, J2 square lattice model. Yeah, so that their Hongzhen Jiang's phase has similar correlations as our phase around T2 over T1 equals 0.3.
I see. Okay, thank you. I think that makes sense. Okay, thank you so much.
Thank you.
So, Steve, you have a question?
Yes. Let's see. About I don't know, 35 or 40% of the way through your talk, you showed the sort of charge density waves where it was 2 holes per stripe and 4 holes per stripe. Can you go back to that one?
Yes. Sorry, sorry. Crashed my, let me open it again. It seems I cannot move it faster than it crashed, but here.
You'll have to share again.
Yeah. Oh, share. I forgot to share. I see. Am I still inside? Oh, I'm still inside.
Yeah, but we cannot see your screen.
Oh, okay. Yeah. Okay. Oh, okay. I start the sharing. Share this. Yeah. sorry. Couldn't be completed. Can you see my screen now?
Well, half of it. Yeah, now we can see it. Yeah.
Okay.
So I'm looking at the left side and I'm comparing the top panel and the bottom panel, and you know, so we see this huge difference in the amplitude.
Yes.
That is, you know, if you look at the scale.
Yeah.
So what I wonder is the bottom one just Friedel oscillations instead of stripes?
Yes.
And you know, can you measure to look for any sign of a pi phase shift across a bump? Look at the correlation function on two sides of a bump to see if there's a pi phase shift, which we would probably see on the top one and not on the bottom one.
Yeah, so the phase shift, I haven't done that kind of measurement. I can check. So we the bottom one has very small amplitude, so it's not strong stripe. But from the correlation, the density correlation has a power law behavior with the exponent somewhere around 1 and 2.
Right. So that's roughly consistent with it being, you know, a much weaker effect, you know, Friedel oscillation sort of thing. Yeah,
Yes.
yeah.
Yes.
Right.
Yeah.
Okay. Thanks.
Thank you.
So Anas, you had a question?
Yes, thank you. It is just a general, or maybe very general question. So the Hubbard model in the 2 dimension, it's a model for the copper oxide, and the other atoms is I think it's only included as a dopant, so for the doping. So my question is there another much more direct effect of the other atoms on the modeling of the cuprate?
Yeah. At least we need to consider cuprate and oxygen. However, the one band model is a minimum model where you treat the charge as moving on the cup side. So is that your question?
So now this is only the influence as a dopant. So this is only
right. Yeah.
And there is no other contribution from them.
No, so that's not considered in that kind of one band model.
And so why so my question is why? So I want to understand it.
Because even just Hubbard model, one band Hubbard model, it's not very easy to get a conclusion what's going on. So then the more realistic model may be harder to get concrete results. So, which is the reason many people study one-band model, but there are also groups study two-band models.
Okay, thank you.
Okay, so maybe last question for Jan.
Yeah, thank you, Donna. Very nice talk. So my question is, you enforced SU2 symmetry to get these very large bond dimensions. Now, to what extent does enforcing SU2 symmetry change the observed behavior relative to computations that only use U1 symmetry?
So we actually initially did a lot of calculation use U1 symmetry. For that state, that system, we always get the same results. If you have a system which has much stronger like magnetic order than the SU2, doesn't allow the spin symmetry breaking, then sometimes you don't get better results from SU2. But for that model, I think we always get the same thing as the U1 system.
So is the reason that if T2 is large enough that you have a frustrated system anyway, then the system does not have this tendency to break SU2 symmetry spontaneously, and therefore the results are the same? Is that what you're saying?
I think the doping plays very important role because we also consider very small T2. And also we are doing the 4-leg and the 6-leg cylinder. I think if we compare with the 8-leg results, maybe spin correlation becomes more important.
Okay, thank you very much.
6-leg, somehow the spin correlation turn out not so strong.
So I see that Andreas has probably a comment on the comments.
All right, thanks. Just out of curiosity, if you use 20,000 SU2 multiplets, how long is the calculation running?
The 1 point if we do 20,000, we run about 3 months. However, we are not doing the parallel calculation. I heard from Hongzhen Jiang they are using, they can use different nodes to do parallel. We are only doing parallel on 1 node.
Fine. And so I understand you worked very hard trying to converge and extrapolate the data, but still for the 6-leg ladder, you still see a lot of variations in it.
Yes.
And so you had one slide, I kind of missed it in terms of discarded weight. So what's a typical discarded weight that you could reach?
Typical is 10⁻⁶. So that's one, 10⁻⁶ for I think for 1/6 doping, that's truncation error becomes slightly larger, but we can reach 10⁻⁶.
And so do you have an understanding, you had a scaling of the exponent of the superconducting correlation versus dimension, and you had an exponent there in a sense that the exponent was changing, it kept changing its slope and whatever. Whatever you did in terms of D, do you have an understanding why this converges so slowly? And in particular that the exponent basically, it seemed to show a linear behavior.
Yeah, so that is because we have typical mechanical state and it doesn't converge until so we did that kind of plot for 4-leg ladder. In that case, initially it increase powerfully, then it saturate. So for 4-leg ladder, we only need to keep 1 order of magnitude smaller band dimension. Let's say only need to keep 10,000 U1 state to get converged results. But on 6-leg ladder, the entanglement is much harder to capture. So I'm also thinking, looking at the local probe, it's really interesting if we want to do the wider systems. Yeah.
Okay, so the really last question now from Steve.
Yeah, so there's a, these are very impressive calculations. Looks like very high quality DMRG work. The problem that, you set yourself is perhaps somewhat harder though than it might have been, because you're really trying to understand the infinitely long cylinder with width 6 with these very slow power law decays, and that makes it very difficult. And so so you've done a great job on that. The other philosophy that you can have is, well, is the really long asymptotically 1D system the shortest way to understand 2D behavior? And so the other way that you can do is you can take much shorter systems and try to and in shorter systems, then you're not really trying to find those power laws. You're just, in 2D, it's very likely to order, at least in many orders. And so you can just try to find the order. And that can be just sort of an easier job to do. So I guess there wasn't really a question there. That was more of a comment.
Okay, but I think we are all overwhelmed by all the graphs and the numbers and the bond dimensions. So I think this is a good time to stop and thank Donna for this talk with these great results. So and a great talk.
Thank
so thank you so much, Donna. I think we will see each other in next month for the next instance of the European Tensor Network colloquium. Although, Frank, do we have one actually before summer, or do we kind of have the next one after summer?
Well, I was thinking maybe we could have one last one in July.
Yeah, very good. Let's